Okay, so again, we're going to go ahead and talk about lesson 51 today, which is how do you find the area between two curves. The hardest part of this by far is graphing each of the functions, but like I just said, I did that part for you. So let's make sure we understand what's what. So before we find the area between two curves, we're going to go back to what we've been doing, which is finding the area under the curve, which is pretty much exactly what you did on our most recent test. So first, y equals x squared. Please note that that is the quadratic in blue. It faces up, of course, and goes through the origin. Then notice your second y equals. This second y equals is y equals 0. That is this horizontal line on the x-axis. Then notice you have each of these x's. X equals 0. That is this red vertical line. And x equals 2. That is this purple vertical line. So again, in another life, you would have had to graph all this on your own, but to save time, I graphed it for you, so you're welcome. What you do have to do is you now have to shade the region that is bounded by all four of those curves. So it has to be under the blue curve, it has to be above the green curve, to the left of the purple curve, and to the right of the red curve. The only region that fulfills all those requirements is right here. So go ahead and shade this region. This is what we want to find the area of. And again, I wanted to start us off nice and simple, and I wanted to start us off with something that is familiar. So you're trying to find the area of that pink region. Because we are lucky enough to have this y equals 0, I actually don't have to do anything different than what I've been doing, and I'll explain why in just a minute. So we're going to go ahead and set up an area equation to find the area of that pink region. You're going to set up a definite integral. Not only do you have to be able to graph these, even though I did it for you, you also have to be able to identify the points of intersection. So those points of intersection are shown to you. Here is one point of intersection, 0, 0. Here is the other point of intersection, 2, 0. And the third point of intersection, 2, 4. So that's where all four of the lines meet up. When you go to set up your definite integral, from what x to what x does that pink region exist? Tell me. 0 to 2. 2. You have one on your paper. It's okay. All right. You're trying to find the area under the blue curve. The blue curve is x squared. And then, of course, remember when you integrate something, you must have a variable of integration, which in this case is dx. Then you solve it just like we've been doing. How do you integrate x squared? X to the third over 3. You are going to evaluate that from 0 to 2. Which of those numbers do you plug in first? The 2. If you plug in 2, cubed is 8 thirds. The fundamental theorem of calculus is always a subtraction. Then you're going to plug in the bottom 0, get a 0. 8 thirds minus 0 is in fact 8 thirds. Something to note about this, this is the entire positive area because again, it's all above the x-axis. So this is the positive area, total positive area. So it doesn't seem like that's different than what we've been doing. So why is that actually different? So this is not just the area under the curve. It's the area between two curves. And the two curves in question are y equals x squared. We'll call that y1. And y2 is just y equals 0. So technically what you just did is you found the area between the blue curve and the green line. Because of the fact that the green line was 0, you didn't actually have to set up an extra step, but you will in every problem going forward. So first, just make sure you understand the basics. Understand why the graph looks the way it did. Understand why I shaded the region that I did. Understand why it's 0 to 2. Understand why it's 8 thirds. Yes, question? Mm-hmm. If you really can't wait and be quick, okay, take that pass with you that's hanging. So again, if you are finding the area under the curve, you can extend that definition to be the area between two curves. And the two curves in this case are the x squared and the 0. So what if one of the curves is not 0? Well, here's kind of the main event for today right here. So if the bottom curve is not 0, then you have to subtract before integrating. When you subtract, you always do the top curve first. So we're going to call that your f. Then you're going to do your bottom curve second, which we're going to call your g. So again, for all these problems in lessons 51 and 52, when it says to find the area between two curves, and it's today, you have to always do the top curve minus the bottom curve. Sometimes the top and the bottom change throughout the interval. So sometimes you have to break it up, but we'll start off with some nice and easy ones. So again, this is the formula for the area between two curves. This is from the starting x to the ending x. The f is the top curve, the g is the bottom curve. Again, if you have the graph in front of you, which I've made for you, this is actually very simple. So let's try another one. Go ahead and turn to number 2. Again, here you have 4 different quantities, all of which I have graphed for you, but let's make sure we know what we're looking at. So find the area bounded by these 4 things, starting with y equals x squared plus 2. Mine is colored, but yours isn't, so feel free to color code it if you want. Y equals x squared plus 2, that is this upward facing quadratic. Then y equals negative x, that is this diagonal line with a negative slope. X equals 0 is the red line, vertical. X equals 1 is the second purple vertical line. You need to highlight the area that is bounded by all 4 of those curves. So if we go ahead and highlight that area, it's in here. Again, the area that you shade has to be contained on every side. So if one of the sides is going on forever and ever, you know you've chosen the wrong region. Make sure you're shading just so that when you go back later, you know what it is you're looking at. And then for that particular region, you are going to have to subtract before you integrate the top curve minus the bottom curve. Sometimes the top curve and the bottom curve are the same the whole time, and sometimes they swap. In this case, it's the same the whole time. So this green curve is the top curve for the whole time. This blue curve is the bottom curve. So T for top, B for bottom. How do I know that for sure? If you were to draw vertical lines in this region, it would always go from the green curve to the blue curve, so the top curve to the bottom curve. Once you have highlighted the region, once you have identified top and bottom, go ahead and set up your area. So A for area equals the integration. Look at that pink region. Look at the points of intersection that I have shown you. From what x to what x does that region exist? It's just 0 to 1. Per the rules, you have to take the top curve, which is x squared plus 2. Then you have to subtract, that's the rule, you subtract the top minus the bottom, and the bottom curve is negative x. So again, if you can look at it and see the top curve and see the bottom curve, no big deal. Now let's go ahead and simplify this. So this becomes the integration from 0 to 1. This double negative makes a positive x. So I'm just going to write this with the x squared first, the positive x in the middle, the 2 in the back, and again, you really should finish it with the dx. I didn't take any points off on the test if you forgot your dx, but it really should be there. Top minus bottom, simplify, now integrate. How do you integrate x squared? Cubed over 3, squared over 2, 2x. Evaluate that bad boy from 0 to 1. What number do I plug in first?
1.
The 1. So everywhere there's an x, put a 1. That's going to give me a third plus a half plus 2. The fundamental theorem of calculus always says subtract. And then everywhere there's an x, put a 0. Again, doesn't always turn out to be this way, but in this case it is in fact 0. Then you need to calculate this green answer. You can do so with a calculator. You can give me the answer as a fraction or decimal. And if you do that, it is 17/6. Again, you can write it as a fraction or a decimal. I do not care. Probably good to notice here that that's not entirely positive. Some of it is below the x-axis. So some of the negative cuts off some of the positive, and that's fine. Questions? Again, it really is fairly straightforward, I think. Yes. So look at the pink region. You have to do the equation of the top curve minus the equation of the bottom curve. So the top curve is the green one, that's x squared. The bottom curve is the or x squared plus 2. I mean, we'll do a few more, you tell me. Okay? All right, let's try number 3. Find the area between the following graphs, and here there's only 2 of them. So first, x squared plus 2x plus 1. That is clearly the blue quadratic. Then 2x plus 5, that is the red linear equation with a positive slope. Note those points of intersection. Again, normally you might have to find them for yourself, but I did them for you, so you're welcome. Go ahead and shade the region that is bounded by those 2 things. That's going to be in here. Notice you don't have any x equals or y equals in this problem because you don't need them. 2 curves meet enough for everybody. So going back to what James was asking just a minute ago, if you now need to set up top minus bottom, I do think it's obvious what the top and bottom curve are, but you would have to tell me. So the top curve is the red dotted line, so I'm going to put T for top. Then the blue curve is the bottom curve, the quadratic, B for bottom. And again, how can I be 100% sure that is the top and that is the bottom? If you draw vertical lines through your shaded region, it should always start at the top curve and end at the bottom curve. So from here, go ahead and set up your area equals. Look at that pink region. It exists from what x to what x? -2 to 2. Okay, it's all right. It's all right. Top curve is the red one, 2x plus 5, trying to help you with some color coding. Minus the blue curve is the bottom one, x squared plus 2x plus 1. If I distribute that minus, I get a negative x squared, a negative 2x, and a negative 1. So this is the integration from -2 to 2. This 2x plus 5, this negative x squared minus 2x minus 1, go ahead and combine like terms. So I'm going to put the negative x squared first. Tell me something about these x's. They actually cancel. And then tell me about 5 minus 1. It's 4. And again, you really should dx it. Once you do the top minus bottom, then you're free to integrate and solve, which is just what we've been up to. So from here, you're going to get negative x cubed over 3 plus 4x, going from -2 to 2. Go ahead and start by plugging the 2 in, and just be a little bit careful. When you plug the 2 in, you're going to get -8/3 plus 8. That's just what you get when you plug in 2. Always a minus. When you plug in -2, here's where some of you went a little bit awry on the test. So -2, you first have to cube it, which is -8. Then you have to turn that -8 into positive. So it's actually 8/3 minus 8. I'm going to change this 8 to be 24/3. So -8/3 plus 24/3 is 16/3. Minus, I'm going to change this 8 into 24/3. So that's -16/3. What happens if you minus a minus? It becomes a plus, 32/3, or the decimal equivalent. 10.67 repeating. Yeah. So that's what the homework is. You have graphs that are done. You have to shade the region, identify top minus bottom, subtract, integrate, and get the answer. Before you do that, though, as hard as it gets is the last 2. We're not actually going to solve them. We're just going to set them up similarly to how we did earlier. So take a look, if you would, at number 4. It's probably like 5 more minutes. That's it. Okay. Again, I've tried to keep them nice and quick and easy. Find the area between these two curves, and then most importantly, set up only, do not solve. So you don't have to do all the work, you just have to do the setup, kind of like what we were doing in chapter 4 when the problem got too long. So starting with the blue cubic, 3x cubed minus x squared minus 10x, that is the blue cubic. Then I have the green quadratic, which faces upside down. When I'm trying to find the bounded region, there are actually 2 of them, and I'm going to do them in 2 different colors, and there's a reason, okay? If you don't have colors, that's fine, but here's one of the regions. This region here is bounded by those 2 curves. Remember, it has to be bounded on all sides. And then there's a second region here, and I'm going to put it in another color for a reason. If you don't have colors, that's fine, but I think it helps. Here's why having those 2 colors is so important. Look at the purple region. If you look at the purple region, here is the top curve, and here is the bottom curve. What happens when you get to the pink region? They switch. Now the green is the top curve, and the blue is the bottom curve. So if the top curve and the bottom curve switch places, which is perfectly fine, you just have to write this as 2 separate problems. So I'm going to write one integral for the purple, I'm going to write a separate integral for the pink, and I'm going to add them together. So let's do the purple one first. If I want to find this area, I'm doing the purple first. Look at the purple region. From what x to what x? -2 to 0. Again, this is the purple part right here, -2 to 0. For the purple region, the top curve is the blue one, which is 3x cubed minus x squared minus 10x. Then you have to subtract the bottom curve, and the bottom curve for the purple region is the green one, which is -x squared plus 2x. Could you subtract them, integrate it, and calculate it? I think you could. No. You're not going to for this one. Then it's a plus, and now you're going to set up a second integration for the pink piece. So for the pink piece, what x to what x? 0 to 2. For the pink piece, the top curve is now the green one, so you're going to put that first. Always a subtraction in between. And then the bottom curve is the cubic. Right. And again, you could, I'm fairly confident that you could subtract them, integrate them, and calculate them. It's just more work. It's not harder. It's just more. So I'm fine if you can do 1, 2, 3, that level all the way through. For one like this, I just need to know that you understand why you have to set it up twice. So questions? Okay. Last one then, if you're ready. No questions? Give you 1 second. Looks like a few people are still writing. Bless you. Or maybe not. Okay, I'm happy to go back to this in a minute if anybody needs it. Last one here, I know how much y'all love trig. So here we have a sine and a cosine, but again, we're just going to set it up. We're not going to actually solve it. So given this graph here, note the point of intersection here and here. And it turns out that they actually intersect infinitely many times. The sine and the cosine go on forever and ever, and they keep intersecting. Every time they intersect, they create a region of equal area. We're just going to find one of those regions. They're all the same amount, yes. So the sine wave is the red wave. The cosine wave is the blue wave. There they are. You might not have seen them for a while, but you have seen them. You can choose any of the regions you want. My advice, choose the one that's the first positive. So I'm going to choose this region here. Again, technically speaking, you can choose any of them because they all will give you the same answer. But why not make your life easier and pick the positive one, especially since the points of intersection are there for you? So all you have to do is write me an area equation. You don't even have to finish it. So look at that pink region. From what x to what x? What do the yellow points of intersection say? Pi over 4 to 5 pi over 4. Which curve is the top curve? The red curve, which is the sine. So you're going to do the sine minus the blue curve is the bottom curve, which is cosine. Again, this whole thing should have a dx, and you don't have to actually finish it. You just have to set it up. I mean, yeah, if you don't remember sine and cosine, yeah. So that is lesson 51. If you look in that little packet, you'll see lesson 52. That's tomorrow. Turn again, you'll see homework 51 and homework 52. So you have the rest of the period to do 2 problems. These are the answers, 9/2 and 4/3. Just make sure you can get them. That's all I want you to do for the next 25 minutes. 2 problems. That's it. Okay? Again, tomorrow, very short, easy lesson as well. And I'm not planning anything for Friday. So you're silly if you don't just try to bang these out now. These are going to be your first 2 homework grades of the 4th marking period. Yes.